common questions that are coming up. Again, if you aren't able to write your half reactions to figure out what's oxidized or reduced, you're going to have a bad time. That is your foundational skill here. So I really recommend, going home if you're having trouble with this, hitting the homework questions that have you write half reactions pretty hard. Okay, so here we go. We've got our two reactions here. So I'll go ahead and write my half reactions. So I've got oxygen, gas, H plus goes to 2H2O, liquid. Okay, great. All right, is this happening at the anode or the cathode, this particular reaction?
Anode.
Not sure. Okay. Oh, what, huh?
Anode.
The cathode, yes.
Cathode.
Okay, this is cathode. Reduction is happening here.
Sort of.
All right, so I can go ahead. I know I'm going to need my reduction potential, so I can go ahead and look that up here. Just make sure that, right, my reduction potential should be 1.23 volts. You guys checking me? Make sure you do that. That's peroxide. Where am I looking? Yeah, there we go. Okay, great. All right, so let's write my other half reaction. I've got 4 silver goes to 4 Ag plus aqueous 4 electrons. Where's this occurring? The anode or the cathode? It has to be at the
Anode.
Anode, yeah. Okay, so my reduction potential here. Right, and again, since this is oxidation, you're going to want to look at the opposite reaction that's happening here because these are all reduction potentials. We don't measure oxidation potentials. Yes?
Why didn't you write plus 4 electrons?
Oh, shoot. Oh, no. I left them off. Thank you. Sorry about that. No, that was my mistake. Thank you for catching that. Yeah. So plus 4 electrons here. Okay, great. So, where was I? Oh, yeah. Okay. So here I look at my reduction. When you're looking at reduction potentials and that number, again, stoichiometry does not matter. So my reduction potential here, plus 80 volts. Okay, great. Now I'm being asked in this problem to find my delta G. So I'm going to use this equation. Delta G equals negative number of electrons that are moving times Faraday's constant times my cell potential. And since I'm looking for a standard delta G, I can use a standard cell potential. All right? So I know I can calculate a standard cell potential. Right? E cell is going to be E red for the cathode minus E red for the anode, which should be 0.43 volts by the time I subtract here. Right? And all I've done is 1.23 volts minus 0.80 volts. Okay? All right, great. So I've got my cell potential. I know Faraday's constant. All I need is that number of electrons that are moving. Now, when you're looking at the moles of electrons that are moving, stoichiometry does matter in this case. If you're just looking at E red, you can ignore stoichiometry. But here, since we're trying to find number of moles, we have to pay attention to stoichiometry. Now, some people were asking about this. They said, do you have to add these two numbers together? Is the number of moles of electrons actually 8?
No.
The answer is no. In this case, N equals 4. There are 4 moles of electrons because those electrons are the same ones. They're just moving from one place to another. These electrons are moving here. They're the same electrons. So the answer is 4. 4 electrons. 4 moles of electrons. Okay? All right. So I've got number of moles of electrons. I know Faraday's constant. Great. I know my cell potential, so I can find delta G. Delta G equals negative 4 moles of electrons times Faraday's constant, 96485 joules over volts times moles times my cell potential, 1.43 volts. All right, let me just make sure I've done this right. Moles, volts. Look, the joules, that sounds great. Okay, so I get negative 1.7 times 10 to the negative. I did that in pencil, so it's hard to read. Joules for my delta G. Is this a favorable reaction?
No.
Is this reaction based on the sign of delta G? Is this thermodynamically favorable?
No.
Yes,
Yes.
it is. Yes, sir.
Thing.
Oh no, did I do this wrong? Oh, is it, oh, to the fifth? Oh, sorry. Okay, thank you. Positive 5? Sorry, that must have been a stray pencil mark or something right there. My bad. All right, is that right now? You guys agreeing with me? Negative 1.7 times 10 to the negative 10 to the fifth joule? Okay, sweet. Yes, ma'am. Yes, in this case though, we don't really have a whole lot that we have to go on. Oh, sorry, where was the person asking? Okay, thank you. So in this case, we don't really have a whole lot to go on except for those reference values. So that's why we're going to use those. Because we think, yeah, these are all kind of given. The 4 is counted, so that's not technically a significant figure. This isn't really a significant figure at all. So the best that we have to go on, the thing that's closest to being a measured value, is the things in those E-red table. So that's why we go, this is subtraction, so it's to 2 decimal places, giving us 2 sig figs when we multiply. Yeah. Yes, ma'am?
So why is it thermodynamically favorable if it's a negative?
So remember, according to delta G, if you think about delta G and signs, anything that's got a negative delta G is a spontaneous process. So that is thermodynamically favorable. All right. Delta G is 0, then, you know, kind of equilibrium. That's not so great if you're a living thing, right? Delta G is positive. That does something coupled if you're a living thing. All that good stuff. Okay, great. All right, we are coming up on our last topic in electrochemistry. This very last topic is something called the Nernst Equation. Last topic. All right. And we're going to want to use our chromate equation. Yeah, so we'll use that. Okay. Okay. I'm not going to take you actually through deriving all of this. I guess I could, right? That was like, I could hear the pain that was emanating from you. Okay, well, since it's 8 o'clock, I'll go ahead, if you are interested, you can follow through either in the PowerPoint slides or in the book. I think it's kind of interesting to show how we get from one place to another, from like where we started all the way back at the beginning of this and now into the Nernst equation. But I would go ahead and just show you, I'll show you the end of it. How about that? The end of the Nernst equation. Let's go here. Now, the whole reason why I ordinarily would take you through this derivation, it's not that long at all. The whole reason why we're going to talk about the Nernst equation right now is that now, for the first time, we are going to have the ability to find cell potential under non-standard conditions. So that's the whole point of this, right? And I just want to be really clear. The whole point of us doing this is so that we can find cell potentials under non-standard conditions, right? So look here. We've got E, whatever cell potential we have is equal to our standard cell potential minus N, right? Okay, so that's number of moles there. Log Q. What is Q? Reaction quotient. Ooh. So we're going to need a piece from equilibrium now, from our equilibrium chapter, to come back into the Nernst equation here. So again, why would we care about this? Why do we care about finding things under non-standard conditions? Do you think if we're finding like membrane potentials, right, across a cell membrane, do you think that all the concentrations are at 1 molar? No, of course not, right? Do you think that the temperature is always going to be 25 degrees Celsius?
No.
No, of course not. So we need a way to work if we've got varying levels of concentration, which is where Q will come in. Q will help us with differing concentrations. And then that T up there will help us at different temperatures. Now for us, we are going to be working only at room temperature. So that's where we differ from biochemists, right? Since we're only working at room temperature, we don't need to worry about multiplying by T. We can go ahead and use this more simplistic form that's down there at the bottom. All right. So what I want to do, what I think I'm going to do is actually just, I'll walk you through how to solve this problem. It's pretty, well, I'll have you guys do pieces of it, but we'll kind of do it more together. The equation that I want to use is actually this one. So back when I said, this chromate one, I said we were going to come back to it. Right? So we're looking at this one here. So you can flip back in your notes. We're using this equation. Now let's say that we're interested in finding what the cell potential is, but we don't have concentrations equal to 1 molar. We're going to mix it up a little bit. So we found our standard cell potentials here already. Okay, great. But let's go ahead and change some of the concentrations of the reactants. All right, we've got chromium is 2 molar. We've got concentrations of hydrogen ion is 1 molar. Concentrations of iodide is 1 molar. And let's say our concentration of chromium cation is, gotta make sure my pencil marks are not. Yeah, don't write something in pencil and then run through the rain. It's kind of a problem. And it's a -5 molar. Okay, so I've got some concentrations here that are not all 1 molar, so that means we're not at standard conditions. That means that this here, my standard cell potential, is not the actual cell potential that I have. So what I need to do, we're going to assume temperature is 298 K, so I can use this version of the Nernst equation. That, again, that is a good assumption for this class. When you get up into other levels, you might have to incorporate temperature, but for us, we can go ahead and use this. All right, so in order to do that, we need to write an expression for Q, right? We're going to need to find N, too. We can get to that. We also need to write an expression for Q. Go ahead and, based on this equation right here, write what your expression would be for Q. And if you're able to actually solve what Q would be, what the value of Q is. You don't have to take the log of it, just find Q. When you're writing Q, is it any different in terms of setup from writing an equilibrium constant?
No.
No.